Modern global web applications manage millions of concurrent user interactions every second, generating petabytes of raw event data. To build the backends that handle this throughput, engineers standardly write code using object-oriented programming paradigms. Object-oriented code organizes data hierarchically in memory. A student object branches into a nested array for courses and a sub-object for an address. To save this permanently, it's handed to a relational database. Relational architecture rejects hierarchy. The object shatters into rigid tables, rows, and columns. The single logical business entity defined in the application code is now physically fractured across multiple disjointed locations on the storage disk. This structural incompatibility between hierarchical in-memory objects and flat on-disk tables is known as the object-relational impedance mismatch. It creates constant friction in back-end engineering. To integrate these two structural environments, developers use an object-relational mapping, or ORM, software layer. The ORM acts as an automated translation engine. During every read and write, it maps the hierarchical code to the flat database tables. This translation incurs a steep read penalty. To reassemble one student object, the database cannot fetch a single file. The database must execute multi-table join operations, scanning across these students, addresses, and enrollments tables to match foreign keys and stitch data together. Saving triggers a write penalty. The system locks rows and executes write commands across multiple tables simultaneously to maintain strict references. While ORM tools function for small applications, the CPU overhead required for these continuous translations degrades query latency under heavy traffic. To eliminate this performance bottleneck at enterprise scale, engineers must stop translating objects to fit tables and instead abandon the relational table entirely. The architectural alternative that bypasses these relational constraints is the document-oriented NoSQL database, such as MongoDB. The core operational philosophy of a document database is encapsulation. It stores all related data for a specific business entity within a single self-contained record. This is achieved using JSON, or JavaScript Object Notation, a text-based, language-independent data format. Here is a structured JSON document. It natively supports hierarchies, allowing developers to embed child objects inside curly brackets and indexed arrays directly within a parent field. The object-oriented student model maps one-to-one into this JSON document. No fracturing is required. JSON enforces 6 data types: strings, numbers, booleans, null, objects, and arrays. This maps directly to standard programming memory models. By storing data natively as a nested document, the complex ORM translation layer is eliminated. The database reads and writes entire objects in a single operation. While plain-text JSON is highly readable for developers, it is too bulky for optimized machine-level database storage. To resolve this, MongoDB uses BSON, or binary JSON. It serializes the text documents into a machine-readable format for rapid disk storage and indexing. Abandoning the relational table enables a second architectural capability, dynamic schema support. In a traditional relational system, adding a single new field to a user profile requires executing an alter table command. This locks the database and can cause downtime. A document NoSQL collection operates differently. Records within the database do not share a predefined structural blueprint. Looking at this collection, document A has 4 fields, while document B has 7, including entirely new attributes. Both documents sit side by side without triggering errors. This schemaless flexibility allows development teams to execute rapid code deployments without waiting for database migrations. In database architecture, eliminating constraints always introduces new trade-offs. Bypassing the relational table requires sacrificing the strict guarantees of multi-record transactional integrity. Relational databases enforce ASIC properties, atomicity, consistency, isolation, and durability to guarantee absolute data accuracy across linked tables. This matrix contrasts that standard with the base paradigm adopted by most NoSQL architectures: basically available, soft state, and eventual consistency. The base model trades instant consistency to maximize continuous uptime and write performance across distributed nodes. Eventual consistency means the system guarantees all nodes will eventually sync up, even if they return slightly outdated data for a few milliseconds during high traffic. Choosing a document NoSQL database means accepting these relaxed consistency rules in exchange for high partition tolerance and speed. These competing models dictate how the hardware scales to handle increasing traffic. Because relational systems rely on strict table joins, they scale vertically. Engineers can only upgrade the hardware components of a single server. Document NoSQL is built natively to scale horizontally. Independent documents are distributed across a cluster of commodity servers. This topology shows horizontal sharding. A central router node intercepts incoming BSON documents and uses a shard key to balance read and write traffic across multiple server nodes. This linear scale-out capability allows systems to handle petabytes of data without hitting a single machine hardware bottleneck. If an application handles banking ledgers requiring strict transactional integrity, the relational table remains a requirement. But for web applications and global systems demanding rapid scalability, mapping application objects directly to a document database resolves the impedance mismatch. This architecture provides a frictionless data infrastructure, allowing modern systems to operate at peak performance across distributed networks.